All right, we are back. Last episode, we have done the following. I can just look at the git logs. Amazing. Oh, so that's what we added last time. We are now parsing both the head and the maxp tables from the file into separate structs that make it easier to access all of the data. The advantage of this, I was just thinking about this before the episode start. The advantage of doing it in this composable way is that if someone wants to add their own table or like their own maxp version, they only have to write their own variant for this part. They just define their own maxp thing and then interpret it from the bytes and do whatever they need, instead of having this like be returned all at once. We just do it in parts, if that makes sense, because this is where you start parsing the file with the table struct. You get all these tables, but the tables haven't been parsed yet. You can choose which ones you would like to parse and how you would like to parse them. So that's nice, I think. There's probably more advanced, better designs of this, but for now this works very well for me. And then I was watching one of the episodes, or the last episode, and then I noticed I had made a copy paste error. I had the little endian thing defined as from big endian bytes, and should have been from little endian bytes, obviously. So I fixed that, and yeah, no unit tests. Bad, but we don't want to be slowed down by unit tests if we're still developing the code super fast. Anyway, what are we going to do today? So the goal for now is to read the glyph table. And we were looking at this last time, and we noticed we need to parse the maxp table and the loca table. To parse the loca table, we needed to parse the head table. So next up is parsing the loca table itself. And what does it contain? Well, it contains a mapping from index to location. Then what is an index? I think the index is probably the like the character code, the Unicode character code is what I'm guessing. But let's read this. Relative beginning, compute length, last. So it's a bunch of offsets where the length is specified by the difference between two consecutive offsets. And then there's a missing character, an outline, a space character. So characters that do not have an outline are simply two offsets, one after the other, pointing to the same location. So that makes the length equal to 0. And then so the reason we needed to parse head table is to figure out, are we using the loca table that uses the small indices of 16 bits, or do we have a 32-bit indices table? And for the file I'm parsing right now, which is the source code variable font, we seem to have a 16-bit table, but shouldn't count on it. So what does this mean? Offset 16 offsets n, where n is numglyphs plus 1. The actual local offset divided by 2 is stored. The actual local offset divided by 2. So that means every glyph is at least 2 bytes, or 0, or a multiple of 2 bytes. Is that right? Okay. Well, let's see what we can do. Let's create a 16-bit version of the locat table. Or do we need to do that at all? We can just parse a slice of offset 16. Let's have a look at what offset 16 means exactly. Alright, so data types. Offset 16. Same as uint 16. Null offset is 0, 0, 0, 0. But then this must be local to the table, right? This cannot be an offset within the file. It has to be an offset within some table, because otherwise, yeah, that's more space efficient, because that makes it more likely you can use 16-bit offsets. So let's try to do that. So we just gonna hack it for now. Buffer is read only. Oh, we're in git, some git thing. So what we can try to do is loca is a reference to a slice of 16 big endian values, and we compute it by doing, we take root dot loca bytes. We need it, so we just unwrap it, panic if we don't have the table, and then consume a slice of what length? Well, the length should be head table dot no, it's in the maxp table. Dot glyph numglyphs. Maxp dot numglyphs. Let me create a function to extract the data, since it's available in all variants of the enumeration. And we have to make this into a usize, so we do u16 from this as a usize, and then we must implement unwrap. They have to implement raw expected reference found enumeration. We also unwrap that. Well, we should do the OK or error thing, right? Or or unexpected end of input. Nice, I have tab completion. Then we need to implement the raw from raw bytes trait for U16VE. Yeah, exactly. Format the thing. Yeah, that's what we have to do. So we go into... Oh, I hate it when this happens. I can't change files anymore. Yeah. Oh, Emacs. Oh, SpaceMax. Oh. Right. Not very happy about that. It does work now. So here we have to find a trait. All right, we're gonna move it into utility. Some utility thing, and here we do unsafe implement from raw bytes for TE. This will be like that, and then back to main. Pop mod util. I don't know if I want to make that public. I don't think so. Not yet, at least not until we refine it. This trait. And this probably too. Create a file. util.rs. Make it public. Public. Take this out. Public. Public. I don't have to do that since the trait's public. That's it. This can also go into num. Just doing a little bit of cleanup. And there's our thing. The fixed point number that we haven't defined any operations on. Use create utility. Shouldn't this be create.num? Yeah, I think that's better. Does it still compile? It does. So do that. Move utilities into its own crate. Well, good. So now it's actually, and actually this is +1. Should not forget that. Let's see how that goes. No lookout table available. Oh, there's no lookout table. That has to do with the font file we're using. So it's using some other way to represent things. So I know that it's using this C. What are you? CFF2 compact font format version 2 introduction. It is intended for use only in the context of an OpenType font as the SFNT table with tag CFF2 depends on data and other OpenType tables. All the data from the 1.0 format that is duplicated by table number by data and other tables, or which is not used in context of an OpenType font, is removed. So it's an improvement on version 1.0, mostly in reducing the redundancy. That's what this tells me. Another difference is that new operators are added, and char strings are represented differently. I don't know what that means. And there's a data layout. Okay, so let's have a look at the table? SNFT, SFNT. This one. What? Where is it? There's only one. Oh Lord. I have no idea what we're gonna do now. I think I'm stuck. What I'd like to do is sort of get a print of the table records. See what information we do have. I thought I added the thing. Alright, what do we have in this thing? We have a base record, which is 70 bytes, maybe? Or 70. Yeah, 70 bytes. We have a CFF2 table, which is fairly large. There's the dsig table, gdef. That might be glyph definitions, glyph positions, and the glyph subpositions. hvar, I don't know. mvar, horizontal, I don't know what that means. os2, I don't know, it's pretty short. Then there's stat, svg space, avar, cmap, fvar, head, htmx, maxp, post. Well, we have a ton of stuff. What we can do is just start reading all of these and keep a description of them for ourselves. So let's look at this. Base. Baseline table provides information used to align glyphs with the script size in a line of text. Whether the glyphs are the same font or different fonts, improved text layout. Baseline table also provides minimum, maximum glyph extent values for each script, language system, or feature in a font. Lines of text composed with glyphs. Alright, I think so. Baseline table. Alignment. It's an alignment table. CFF2, we just looked at that. dsig. D. dsig. Dsig table contains the digital signature of the OpenType font. I'm not interested in that, I don't think. Signature. I'm not interested in that. I don't care about verifying whether a font is something trusted. Then gdef. There we go. Glyph definition table. Various glyph properties used in OpenType contain 6 types of information in 6 independent subtables. And has 6 subtables. gsub, gpos, gstf are related. A client may use one or more of these 6 gdef tables during text processing. This overview explains how each of the 6 tables are organized and used. The rest of the chapter divides the individual gdef header, glyph class, attachment point list, ligature caret list, Mark attachment, mark glyph set, item variation store. Right, and there's details on exactly how that works and what everything means. What's next? GPOS. GPOS. Glyph position table. A glyph positioning table provides precise control over glyph placement. Alright, nice. It has all these diagrams and illustrations on how it works. What else do we have? G-sub. Glyph substitution table. The G-sub table provides data for substitution of glyphs, appropriate rendering scripts, cursively connecting forms in Arabic script, or advanced typographic effects such as ligatures. G-sub. So it's about sort of merging multiple glyphs into a single character that has a better shape and nicer. Make the text look nice. G-sub. What do we call it? Glyph substitution. I already typed that. What am I doing? HVAR. Horizontal matrix variations table. I have no idea what that means. Using variable fonts to provide variations for horizontal glyph metric values. This can be used to provide variation data for advanced widths. I don't know what the HMTX table does, and I don't know what left and right side bearings are. I have to figure that out as well. So, side bearings, what exactly is that? And then glyph bounding box, what is that? Well, then we have mvar. Provide various font white metric values found in the OS2 table and other font tables. All right. Item variation store. There's so much stuff. So much stuff. Then OS/2. OS/2 and Windows metrics table. Wow. Okay. What does this tell us? Version. X average char width, width class, subscript type. A whole bunch. Unicode range 1, 2, 3, and 4. What does that bits thing mean? This is one. This is one. Yeah, an unsigned 128-bit number. Big Endian. Vendor ID. Break chart. That's nice. That's good to know. Right, so it is OS2 metrics, sort of like general metrics. Okay, good enough. Stat, what are you? Style attributes table. Style attributes table describes design attributes that distinguish font style variants in a font family. Association. A font family is a set of font faces that share the key aspects of the design. So then what does that mean? Version. Axis value. Oh, this is like, is this where you can change from italic to non-italic and from light to bold, like font weight, that sort of thing? This is an interesting table. Yeah, there we go. Font weight. Editable access value name. Linked value. Right. It's like, okay, so how do we call this? What do we call this table? What does it contain? That's pretty accurate. All right. There's an SVG table. Scalable vector graphics. No. No. But it's only 6,000 bytes. Why is that in this font? They're all black. Isn't that... This is like a text format, right? You gotta be kidding me. Alright, I don't know. I don't think we're gonna... I hope we don't need to use that. That's what I hope. Avar. There's Avar CMap Avar. This looks like style. Oh, so one thing that's very much possible is that in order to support multiple rasterizers, the font file generators might save the font in with as many possible definitions as possible, like duplicate data and store them in different tables, the same information in different tables, so that it's more likely that the rasterizer will be able to load everything, which is inevitable given how complex, maybe not, well, it is complex, how complex this font format is. It's unrealistic to expect everyone implementing a renderer to be up to date and to perfectly parse everything and to also be backwards compatible over many versions. That's not an easy thing. That's a huge development effort. So what they might do is, even though they have new tables, they will still support the old tables so that things still work. And slowly, over periods of 20 years, maybe they will phase out the old ones. I think that's what's going on. Anyway, axis variations table must be used in combination with FVAR. Must use with FVAR. Yeah. Well, we have a CMap. Character to glyph index mapping table. So this is like the look a thing, right? CMap. Character to glyph index. May contain more than one subtable. Alright, let's look at this. This is an important table, so we're gonna read this. This table defines mapping of character codes to default glyph index. Different subtables may be defined that each contain mappings for different character encoding schemes. Okay. Like one table for ASCII, one table for UTF-8, one table for UTF-16, or maybe not. I don't know. Table header indicates the character encodings for which subtables are present. Regardless of the encoding scheme, character codes that do not correspond to any glyph should be mapped to glyph index 0, not def. Each subtable is in one of the seven possible formats and begins with a format field indicating the format used. Ooh, there's 7 subtable formats. Not cool. Format field, yeah. Alright. First formats 0, 2, 4, and 6 were originally defined prior to Unicode 2.0. These formats allow for 8-bit single byte, 8-bit multi-byte, and 16-bit encodings. With the introduction of supplementary planes in Unicode 2.0, the Unicode addressable code space extends beyond 16 bits. To accommodate this, 3 additional formats were added, 8, 10, and 12, that allow for 32-bit encoding schemes. So that's hopefully we only have to care about these. Other enhancements in Unicode led to the addition of other subtable formats. Subtable format 13 allows for efficient mapping of many characters to a single glyph. Okay, this is used for last resort fonts that provide fallback rendering for all possible Unicode characters with distinct fallback glyphs or different Unicode ranges. Okay. Subtable format 14 provides a unified mechanism for supporting Unicode variation sequences. Alright. CMap table version number remains at 0 for fonts that make use of the newer subtable formats. Alright, so the CMap header doesn't change. It's supposed to be 0. That's fine. That is convenient. So we're gonna nominate for decoding. Just gonna do this. I think we want to look at that table first. But let's finish our list. What else is in the file? CMap. We have fvar. Fonts variations table. Oh, yeah, this is what I've seen. This looks like the style and the, what was the other one? Avar. Style, Avar, and fvar seem pretty similar. Let's not read it. There's head, which we've seen. There's HHEA. Horizontal header table. What does that do? Contains information for horizontal layout. The values in the min right side bearing, min left side bearing, and x max extent should be computed using only glyphs that have contours. Glyphs without contours should be ignored. All reserved areas must be set to 0. That makes sense. Major version number of the horizontal header table set to 1. Well, okay. So this is not, this is a simple, I'm going to mark this as a simple table, I think. Should have been doing that from the start. HTMX, horizontal matrix table. Ah, that's why it was simple. Glyph metrics used for horizontal text like glyph fence width, cybering x. This is what? Glyph CFF or CFF2. Wait, what? Let's read this again. Glyph metrics used for horizontal text layout include glyph advanced widths, side bearings, and x direction minimum and maximum values. These are derived using a combination of the glyph outline data from either glyph CFF or CFF2 and the horizontal matrix table. The horizontal matrix HTMX table provides glyph advanced widths and left side bearings. Okay. This is not, I'm having trouble understanding exactly the purpose of these tables, but we're getting there. In a font with true type outline data. Do I care about advanced widths right now? No, I don't, so I'm gonna not read this. And H bar, actually, probably. This is what I should have been doing all this time. How complex is it? Fairly simple. Simple. H bar. No, what's next? HMX Max P. We got that name. I hope names. Naming table allows multilingual strings to be associated with the open type font. These strings can represent copyright notices, font names, family names, style names, and so on. To keep this table short, the font manufacturer may wish to make a limited set of entries in some small set of languages. Later, the font can be localized and strings translated or added. Yeah. That's interesting for just to look at it for fun. I think it's mediocre. It's just a table of URLs and then yeah, it's like so name table that I always use Control V. So it's simple but long. What else? Post table. Postscript table. I know I'm not being consistent with the naming, but I'm doing this on the fly, finding something that I think is useful. There's 4 versions of it. Table contains true type font PostScript printers. Do I care about PostScript printers? I don't know. One of the versions is deprecated. Italic angle and line thickness fixed width. It's simple. It's a simple table. Simple. Cool. Alright, we've gone through the tables that are contained within the file I'm trying to parse. And we figured out that the character to glyph index mapping table is the most interesting to us now, as well as the CFF2 table, which is most likely where all of the character data is, like how to actually draw them. Where are you? Yeah, CFF2. It is the largest table, I think, in the file, so that would make sense. CFF2 compact font format version 2. Complex. Paste that. There we go. So that's most likely our second priority. Hopefully after we understand how to map glyphs from their Unicode, from their character value to some index, then maybe we can use that index to figure out how the glyph is defined and slowly work our way towards decoding this table. But I've looked at the CFF2 table and it looks like it's fairly complex. Essentially, it defines a virtual machine with a stack and operations and a whole bunch of different encodings for operations and numbers that you all need to implement in order to actually read the data. And it's cool because it's very allows you to be it's very flexible, and it's also very compact. But on the downside, it's extremely tedious to parse correctly. That's my understanding, at least. So let's just get started with the CMap. Right. CMap is the character to glyph index mapping table. Let's get a link to that. And start coding. Or reading, honestly. Overview. This table defines mapping or coding scheme. Okay, we read that. The header. Let's look at the header. Struct, derive, debug, represent C. Struct raw CMap header. Version, number of tables, encoding record, encoding records, number of tables. Simple enough. Yeah. Wait, what is the version is always 0. So version is a U16 big endian. Num tables is a U16 big endian. And then we have raw encoding records. Well, let's just stick to the names they gave him, even though they're pretty verbose. With a nice type system, I don't think you need to be that verbose. So it'll have a lifetime referring to the original byte slice, and then we'll return a slice of raw encoding records. but so that's that. And then derive debug strict cmap header. CMap table will have the header, all CMap header. Is this how I want to do it? Yeah, it's nice. And then we'll have the encoding records, and the header doesn't need a lifetime because we just want to interpret that as is. And then we want to define the encoding headers. And hopefully they're pretty simple. From all bytes. And do that for this one too. Header. Encoding records. This is an encoding record. It has a platform ID, which is a 16-bit unsigned integer. There is the encoding ID, which is also a 16-bit, and then there's the offset, which is just 32-bit unsigned big endian integer. From the beginning of table to the subtable for this encoding. Yeah, that's what I want to see. Great. Isn't this supposed to be a encoding record? Encoding header, encoding record. That's why we named it. Do we compile? Yeah. CMap table is never used. And then we will implement how to parse it. For some lifetime A, we will say public function parse from bytes. We will pass it the bytes, and we'll turn self or a parsing error. I'm rusty. Then we get the bytes. Has to be mutable. Well, the slice itself, not the bytes. So that we can consume. And we will first look at the header. So raw C header is raw C map header. Bytes.consume single unwrap. Okay, or parse. Or I'm starting to dislike this because it's the same error every time. Try expression alternatives. Different types. They do? Yeah, obviously. Then if we have the header, we can num tables is u16 from header dot num tables as usize. Let records. encoding records equals bytes.consume slice num tables. Okay, or parse error unexpected end of input. Then we return a CMap table with the header and the encoding records. What's the issue here? It's a reference. And I think I don't need to write it out. Cannot infer type. But you know what you're returning? Strange. I don't see the problem. We can do it by value actually because it's very small. Right? It's like 2 16-bit integers, so that's what we should do. Dereference it, make a copy. And the records, we could return them as a slice. In fact, we have to, because we don't know the size beforehand. So if we were to return it by value, we'd have to allocate a vec. So we have to return that as a slice. And it makes sense too. What's the problem here? Can I move out of bird content? Oh, we have to drive copy. I do it like that. Right. Let's look at the CMap header. Where's our test? Oh, it's up here. Put it at the bottom. Let CMap CMap table parse root meta dot CMap bytes unwrap do that, do that, do that. What's the problem here? We want to pass a reference. It is already a reference. What is the issue? Ah, that's the issue. Okay. Here's the CMap table. Version is 0 as expected, and there's 6 encoding records. And here are the records. We have platform ID 000, 1, 3, and 3. So 0, 1, and 3. Let's have a look at what those mean. 0 means Unicode, 1 means Macintosh, and 3 means Windows. Then the encoding IDs are 3, 4, 5, 0, 1, and 10. Oh, the encodings are different. Wait 1 second. These are the Windows encodings. Byte encoding table. Height byte mapping through table. Segment mapping to delta values. Trimmed table mapping. Mixed. Oh my lord. Oh, right. I'm going to take a small break, and then we will continue.